formal charge is another way of allocating the electrons around a particular atom in a compound. You're probably familiar with the idea of an oxidation number. In those cases, anytime we have electrons which are shared between two atoms, we consider all those electrons to be given to the more electronegative element. So it's a very unequal sharing. In the formal charge, on the other hand, we assume that any of the electrons which are shared between two atoms are shared equally. Now, one of the important aspects of the formal charge is that if we have a choice between two different Lewis structures, we like to have the structure where the formal charges on every single atom are 0. That is usually the best. Secondly, if we're going to have a negative formal charge, we assume that it would be best if that is going to be on an electronegative element, such as fluorine, oxygen, or nitrogen. So for our first example, we're going to look at carbon monoxide and its binding to a metal, because we can better understand the binding of carbon monoxide to metals by using this concept of formal charge, which right away will show us some exceptions to the rule. Okay, so here we have. So the formal definition for the formal charge is that we take the number of valence electrons, and we get that from the group number, the column in the periodic table. We subtract from that the number of lone pair electrons, so those are the electrons which are just on that individual atom, and then minus 1/2 the number of bonding electrons. This minus 1/2 is basically a way of giving half the electrons to one atom and half to the other in the case where they're shared. So let's look at carbon monoxide, and let's look at the carbon atom. Okay. Now we recall that carbon has 4 valence electrons. In this particular compound, we see that 2 of the electrons are just on the carbon. These are a lone pair. And then carbon shares 6 electrons with oxygen. So these 6 electrons in the center are shared between oxygen and carbon. And then the last 2 electrons at the far right are a lone pair that is just on the oxygen. So let's compute the formal charge for each of the atoms in carbon monoxide as a free gas. Well, we have 2 valence electrons. Okay, that's there are 2 lone pair electrons here. We have 6 bonding electrons, so 1/2 of that, 1/2 of 6 is 3. So to compute the formal charge, we start with the number of valence electrons for carbon, which is 4. We subtract the number of lone pair electrons, which is 2, so we have 4 minus 2. We're left with 2. And then we subtract from that 1/2 the number of bonding electrons. So that's minus 1/2 of 6, or 3. So we're left with a formal charge on carbon of a minus 1. So we end up with a minus 1 formal charge on carbon in carbon monoxide. Now we continue with oxygen. Oxygen starts off with 6 valence electrons. It has 2 lone pair electrons, so we start off 6 minus 2 gives us a total number of 4. Then we have to subtract 1/2 the number of bonding electrons. The number of bonding electrons is 6. Half of 6 is 3, so we have to subtract 4 minus 3 to get a positive 1. So in carbon monoxide, the formal charge on oxygen is a plus 1. Now right away, we notice something very peculiar in that we have a negative formal charge on carbon, which is the not very electronegative element, and we have a formal charge of plus 1 on oxygen, which is the second most electronegative element. So we might conclude that this is an inaccurate or invalid Lewis structure, and we'd be wrong, because it turns out, for reasons which are beyond the scope of a freshman course in chemistry, this is the actual structure. We can confirm it by experiment. That's not difficult to show. The carbon-oxygen bond is consistent with a carbon-oxygen triple bond. The easiest way to monitor a carbon-oxygen bond, whether it's a single bond, double bond, or triple bond, is through a technique called IR spectroscopy. And we'll talk about that a little bit further, but we can tell from IR spectroscopy that this is a very specific frequency that is in the range of a carbon-oxygen triple bond. when we have a bond between two atoms, we normally assume that if both of the atoms are identical, the electrons are shared completely equally, and we have a non-polar bond. If we have two different atoms, they're two different elements, we usually assume, and we'd be usually correct to assume, that the negative end of the bond is going to be towards the more electronegative element. So in the case of carbon and oxygen, oxygen has a much higher Pauling electronegativity than carbon, so we would assume that in a carbon-oxygen bond that the negative end of the bond would be on the oxygen and the positive end of the bond would be on the carbon. This will generally be true for a carbon-oxygen single bond or a carbon-oxygen double bond, but will not be true for carbon monoxide. So this is a very important exception to the rule. And because we have this negative end is on the carbon, this is the end of the molecule that invariably will react with metals. Metals tend to be very electropositive. First, they are electron deficient in general, and since they're metals, they easily lose electrons to form cations, and so cations are even formally have a positive charge, so they'll be attracted to the negative end of the carbon monoxide molecule. So when carbon monoxide binds to a metal, it always binds through the carbon end and not through the oxygen end, even though that's not what we might expect from our naive understanding of carbon and oxygen. So now let's see what happens once this binds to a metal. So we've drawn it correctly in that we have the carbon end attached to the metal. For the sake of keeping track of electrons, we're assuming that the metal starts off with 2 electrons. So we're just assuming that it has 2 valence electrons just to keep the number of electrons small so we can keep track of what's going on. So now let's see what happens with the metal. Well, the metal starts off with 2 valence electrons. We have to subtract from that the 2 electrons which are lone pair. So we have the lone pair there. So that's 2 minus 2 is 0. Then we have to subtract 1/2 of the bonding electrons. So the metal has 2 bonding electrons to carbon, so we're left with a formal charge on the metal of a -1. That's a little surprising, but we end up with a -1 formal charge on the metal. So at least temporarily, we've reduced the metal by carbon monoxide binding to it. So let's see what happens to the carbon atom. Well, carbon started off with 4 valence electrons. We subtract the number of lone pair electrons, and that's 0, so still at 4. And then we notice that there's 2, 4, 6, 8 total bonding electrons around the carbon. Half of 8 is 4, so 4 minus 4 equals 0 for the formal charge on carbon. So the carbon formal charge is now 0 upon binding. Let's see what happens with the oxygen. Well, we just compare from what we had before. The situation of oxygen is identical, so let's remind ourselves that we start with 6 valence electrons, minus 2 lone pair electrons gives us 4, and then we have minus 1/2 of the 6 bonding electrons, 3, so 4 minus 3 equals +1. So oxygen still has a formal charge of +1 when the metal first binds to the carbon monoxide. We noticed that when the carbon monoxide first binds to the metal, that the carbon-oxygen bond order stays as a triple bond. And then we notice this is what happens through IR spectroscopy. But then we have a phenomenon where the metal can actually push some of its electron density back onto the carbon monoxide molecule. So one of the ways that we can write this formally is to write it as a metal-carbon double bond. So if we do that, then to keep the octet rule for the carbon and oxygen, the bond order here has to be reduced from a triple bond to a double bond. And we see experimental evidence in IR spectroscopy that this is exactly one of the things that occurs. It goes by the name of back donation or back bonding. So if this situation does occur, let's see what the effect on the formal charge is going to be. Well, the metal has started off with 2 valence electrons. Now it has no lone pair electrons, but has 4 bonding electrons. So 2 minus 0 equals 2, minus 1/2 of 4. So now the formal charge on the metal is actually 0, which is a more reasonable oxidation state, or more reasonable formal charge state for a metal than -1. We know that in general metals don't like to have negative charges. Let's see what happens to the carbon in the center. Well, it started off with 4 valence electrons. It has 0 lone pair electrons, so 4 minus 0 equals 4. It has a total of 2, 4, 6, 8 bonding electrons, 4 with the metal and 4 with oxygen, so that's a total of 8. 1/2 of 8 is 4. 4 minus 4 equals 0, so the formal charge on oxygen has to be 0. Last but not least, let's see what happens with oxygen. Oxygen starts off with 6 valence electrons. It has 2, 4 lone pair electrons, since it has 2 lone pairs. 6 minus 4 equals 2. It has a total of 4 bonding electrons with the carbon. 1/2 of 4 is 2, so we have 6 minus 4 minus 2 gives us a total of 0 for the oxygen. Now, we would know that it has to be true because whenever we have a neutral molecule, the sum of the formal charges on a neutral molecule has to equal 0, in the same way that the sum of the oxidation numbers for a neutral compound has to equal 0. In cases where we have an ion, the sum of the formal charges will equal the charge on the ion in exactly the same way that the sum of the oxidation numbers will have to equal the charge on an ion when we have an ion. And the important thing here is that we see that one way the metal can remove some of the extra electron density that it gains by being bound to by the carbon monoxide is to push it back into the carbon monoxide, and in the process we reduce the bond order from a triple bond to a double bond, and we see two things. One is we get a sort of an ideal Lewis structure where all the formal charges are 0, and we also see strong evidence for this experimentally. Nitric oxide is probably the second most important of the pi acceptor ligands in organometallic chemistry. It has an odd number of electrons, which makes it a free radical. We have a full octet on oxygen, but we only connect 7 electrons around the nitrogen because there are only 11 valence electrons in the molecule to begin with. So now let's take a look at the formal charges on this particular molecule. We notice it's written as a nitrogen-oxygen double bond, and the experimental evidence is consistent with that particular bond order. Nitrogen starts with 5 valence electrons. It has 3 lone pair electrons, 1, 2, 3, and 4 bonding electrons. So to calculate the formal charge, 5 minus 3 minus 1/2 of 4, which is 2, gives us 5 minus 3 minus 2 gives 0. So therefore the total formal charge on the nitrogen is 0 in nitric oxide. Let's take a look at the oxygen. Well, the oxygen has 2, 4 lone pair electrons, 2, 4 bonding electrons. So its formal charge, we get, there's 6 valence electrons. 6 minus 4 is 2. Minus 1/2 of 4 is minus 2. So we get 6 minus 4 minus 2 gives us a total of 0 for oxygen. So the overall bond order, overall formal charge, is a 0 for the oxygen also. So we see that this is a valid Lewis structure because it has an octet around oxygen, as close to an octet as we can get for nitrogen, and we have formal charges of 0 on all the atoms in the molecule. For our next purposes, we're going to look at the bonding of nitric oxide to a metal. Again, surprisingly, it binds through the nitrogen atom, which is normally the less electronegative element. We don't see here any particular formal charge on the nitrogen, but this tends to be the slightly more negative end of the molecule. And we're using a trick here to keep the number of electrons consistent of exactly 1 valence electron on the metal. So here we see perhaps an initial binding of nitric oxide to the metal, and you notice right away that we end up with a lone pair on the metal, a metal-nitrogen single bond, and then the bond order of the nitrogen to oxygen goes from a double bond to a triple bond. So we call this the NO plus binding mode. And let's look at what the formal charges on all the important species are for this particular binding mode of nitric oxide. The metal started off with one valence electron. It has two lone pair electrons and two bonding electrons. So for the formal charge, we get 1 minus 2 is minus 1, and minus 1/2 of 2. So minus 1 gives us a minus 2 on the metal. So we end up with a formal charge on the metal of minus 2. So we see the metal is very strongly reduced, at least initially, upon the binding of nitric oxide. The nitrogen has no lone pairs, but it has 2, 4, 6, 8 bonding electrons. So since there are 5 valence electrons for nitrogen, 5 minus 0 is 5. Minus 1/2 of 8, which is 4, so we get a formal charge on the nitrogen of plus 1. Finally, for the oxygen has 2 lone pair electrons over here, 6 bonding electrons. So for its formal charge, 6 valence electrons minus 2 bonding electrons is 4, minus 1/2 of 6 for the bonding electrons is 3, so we get 6 minus 2 minus 3 gives us a plus 1. So we have a plus 1 formal charge on the oxygen. So this is the NO plus binding mode. And the way we can follow this by IR spectroscopy is that this would change the bond order of nitrogen to oxygen to a triple bond. You see, this does seem somewhat unrealistic in the sense that we have the metal being strongly reduced, and we have formal charges not only on just oxygen, but also nitrogen as well, which are both very electronegative elements. So you might imagine that this might not be a long-term stable binding mode. One way that the metal can cope with this extra electron density that it doesn't really want is to push a lone pair back onto the nitrogen, back onto the ligands. This is the phenomenon which we had previously described as back donation or back bonding. If we do that, we end up with a metal-nitrogen double bond. We reduce the nitrogen-oxygen bond order back down to a nitrogen-oxygen double bond. So let's see what the formal charges on all of these particular species are going to be. Well, we started off with 1 valence electron for the metal. It has no lone pairs, but it has 4 bonding electrons. Half of 4 is 2, so the formal charge on the metal is going to be 1 minus 2 for a formal charge of minus 1. So we see that the metal has been somewhat successful in pushing electron density onto the ligand and off itself. So for the nitrogen in the center, we have 2, 4, 6, 8 total bonding electrons. There are no lone pair electrons. We know that nitrogen has 5 valence electrons to begin with. 5 minus 1/2 of 8, which is 4, gives us 5 minus 4, or plus 1, for the formal charge for the nitrogen. So the formal charge on the nitrogen has stayed the same, plus 1. Last but not least, we can calculate the formal charge on oxygen. Oxygen has 2, 4 lone pair electrons, 2, 4 bonding electrons. So since it starts with 6 valence electrons, 6 minus 4 is 2, minus 1/2 of 4, minus another 2, gives us a formal charge on oxygen of 0 in this particular bonding mode, which we call the NO neutral mode. So we went from NO plus to NO neutral. In the final binding mode, the NO minus mode, the bonding pair that had been part of the double bond between the metal and nitrogen becomes a lone pair on nitrogen. So let's see what the effects of this are going to be as far as the formal charges. Well, the metal started off with one valence electron. It has no lone pairs, and it has two bonding electrons. So 1 minus 0 minus a half of 2 gives us a total of 0 for the formal charge on the metal. So it's been able to go from having a formal charge of -2 to -1 to 0, which is a more reasonable formal charge for a metal. For nitrogen in the center, it has a total of 2 lone pair electrons, 2, 4, 6 bonding electrons. So it has 5 valence electrons. 5 minus 2 is 3. 1/2 of 6 is 3. So we end up with a formal charge on the nitrogen of 0. Last but not least, we look at the formal charge on oxygen. Oxygen has 2, 4 lone pair electrons, 2, 4 bonding electrons. So it's identical to the situation up here, exactly the same bonding situation. So kind of fast forward on that, and we notice that it has to be a formal charge of 0. Now, one of the interesting features of this, which is not obvious from Lewis dot theory, but which we get from the valence shell electron pair repulsion theory, otherwise known as the VSEPR theory, is that now that we have a lone pair on nitrogen, nitrogen becomes effectively sp2 hybridized. So it becomes trigonal planar, and we get a bend. So whereas metal to nitrogen to oxygen, for the first two modes, they're linear. They're going to be in a straight line. But once we get down to here, we go from the metal to nitrogen, the metal to nitrogen to oxygen bond is going to be somewhere around 120 degrees. So there's going to be a considerable bend in the molecule at that point. So that's one thing that we can follow. So the degree of bending in this particular set of 3 atoms gives us experimental evidence as to how much of this electron density that had been put onto the metal can get pushed back onto the ligand. So whereas we can monitor the carbon monoxide back bonding by looking at the IR spectroscopy, looking at the bond order of the carbon-oxygen bond, what we're interested in looking at with the nitric oxide bonding is not so much the bond order, although we can do that, but the degree of bending in that particular bond. Here we have Lewis structures for carbon monoxide at the top and for a particular metal to which the carbon monoxide is going to bind. Now, we have cards in the Pegasus system for metals, but in general, the Lewis dot structure system, Lewis-Langmuir theory, does not work very well for metals. It usually works best for covalent bonding. Except that we can adapt the system. In this particular case, we're going to use the conceit that the metal has 2 valence electrons. So we're basically going to ignore the gray areas in the metal, but we want to look at what happens to the bonding when carbon monoxide binds to the metal. So the first thing to keep in mind is that, as an exception to rules you probably learned, for carbon monoxide, even though oxygen is more electronegative than carbon, the negative end of the molecule is always going to be on the carbon. So therefore, when carbon monoxide binds to a metal, it always, always, always binds through the carbon end, which has tremendous importance in the fact that carbon monoxide is a poisonous gas, and the reason why it's poisonous is because it binds to the iron atom, generally iron plus 2 ion, in hemoglobin, the same part of the hemoglobin molecule which would normally carry oxygen. So it's important it binds to the metal through the carbon end. At first, when carbon monoxide binds to the metal, it forms a single bond between the carbon and the metal using what had previously been the lone pair on the carbon. So we had seen before when we were looking and computing the formal charges, the effect of this step is to reduce the metal. And the metal doesn't like to be reduced because metals like to lose electrons and not gain them. Therefore, the metal will try to relieve that electron density by moving some more of the electrons back onto the ligand. The lone pair that had previously been situated on the metal is pushed to form a bonding pair between the metal and the carbon. So this now becomes a double bond, at least formally, and the carbon-oxygen bond has been reduced in bond order from a triple bond to a double bond. Notice that in this structure, that the carbon has 2, 4, 6, 8 electrons, and oxygen has 2, 4, 6, 8 electrons. So all the atoms have an octet except for the metal, which we are making an exception for anyway. So as far as carbon and oxygen go, they satisfy the octet. And we had seen before that in this particular arrangement, the formal charges on the metal, the carbon, and the oxygen are all 0. So in this particular arrangement, the electron density which had been put onto the metal has been pushed back, at least partially, into the carbon-oxygen bond, reducing it in bond order, and thereby relieving the electron density and the electron repulsion that would have been on the metal. We recall that nitric oxide, NO, has the Lewis structure shown here. It only has a total of 11 electrons. Since it has an odd number of electrons, it's a free radical. We can satisfy the octet rule for oxygen, but we can't for nitrogen. It's essentially 1 electron short. Nitric oxide is perhaps the second most important ligand of the so-called pi acceptor ligands in organometallic chemistry. For the following series, to show the binding of nitric oxide to a metal, we're going to use a metal that starts with 1 valence electron. The reason for doing that is so that we have an even number of electrons throughout. When nitric oxide binds to a metal, it binds through the nitrogen end. And we notice that in forming a single bond to the metal, that the bond order of nitric oxide has gone from a nitrogen-oxygen double bond to a nitrogen-oxygen triple bond. And we might also notice that there is at least a formal resemblance between this particular binding mode, called the NO plus binding mode, and the standard binding mode of carbon monoxide. So notice that there are great similarities between the two cases. This was also the case where the metal is strongly reduced, at least by the point of view of the formal charge, from a formal charge of 0 to a formal charge of -2. If the metal is able to push the lone pair that was here before into a bond with nitrogen, we end up getting a metal-nitrogen double bond, and we reduce the bond order of NO back down to a double bond here. In the process, we were able to reduce the formal charge on the metal from -2 to -1. This is what we had called before the NO neutral binding mode. If one of the bonding pairs that had been part of the metal-nitrogen double bond becomes localized on the nitrogen atom as a lone pair, then we achieve the so-called NO minus binding mode. So in this particular case, the formal charge on the metal has been reduced all the way down to 0, as have the formal charges on nitrogen and oxygen. What this Lewis structure shows somewhat accurately is that when we go to this particular mode, now from metal to nitrogen to oxygen, it's bent, and this is actually realistic. And the previous examples that had shown all 3 atoms being linear, that was accurate as well. So we see that when we finally get to this particular binding mode, if we get that much back bonding from the metal to the nitric oxide ligand, we actually begin to have nonlinearity in this bond. So the degree to which this angle is bent is a way of indexing, a way of telling how much electron density was transferred from the metal to the nitric oxide ligand.